Hello, I'm Michael. I'm a co-founder and chief architect here in Starkware. Today, I will show you how we build systems here in Starkware with Cairo and Sharp. Sharp is our shared prover service. And you will see that you can do it exactly in the same way as well. Let's start. So in these slides, we will show how we can scale a distribute application using Cairo and using Stark proofs. We will use a very simple example of an application requiring a lot of access to storage and it needs to do a lot of store operations. We will guide through and scale it from a very naive solution to scaling storage, to scaling computation, and eventually how we can use Sharp to build a DApp system which is scalable enough to support big storage. Let's start. So the first approach is the most straightforward approach. We have a contract written in Solidity, uses its local storage, and we have some kind of website communicating directly with this contract. This is a very simple design, very simple implementation, very simple operation. This is great. This is perfect, and I really like this approach. But I need to find an issue with it because I have a few more minutes to spare here. So probably, yes, it is expensive as hell to use. You all are aware of the gas cost today, and you know that storage operations are the most expensive operations on the Ethereum network. When there are a lot of calls done by users accessing a lot of storage, it is very, very expensive. Let's see how we can optimize this. So the first straightforward optimization can be to offload the database and move it off-chain. When we move it off-chain, we have to keep the integrity of our application somehow. So we can keep on-chain on the application contract some kind of commitment to the database. It can be as small as a hash digest of the database. And whenever we need to access the database, for example, to read something, we will send to the application contract some kind of witness. We will send to it the value and the witness showing the integrity, the consistency of the read value with the hash. So the most naive solution could be just to send the entire database in the transmission of a transaction, but this is of course very expensive. There are some more there are some better commitment schemes for such a task, vector commitment schemes, for example, Merkle trees, for whom familiar with Merkle trees, but I won't cover it and I won't dive into it in this lecture. So let's now analyze what are the pros and cons in this approach. So first of all, it is really storage efficient. We took all these reads and writes and anything that we need to do with on-chain storage, and instead of keeping a lot of data on-chain, we now have only a single hash on-chain representing the entire database. But what do we get in return? In return, we really get a very complex system design with some non-trivial operation. Before, in the first system that we had, you could just deploy the smart contract, put somewhere the website. It could have been just HTML with JavaScript or something like this, and everything would work. But now we need to have some backend with database. And actually now when there are calls that need to access the contract with operations that need to read or access the storage, they cannot do it directly with the contract anymore. They have to go through this backend. And actually, a lot of user transactions probably become meta transactions in this case. And the operator need to serve them and to send them himself. In such a case, the operator actually takes on himself on all the load of sending the transaction and the gas expenses of these transactions. Moreover, it's not even clear that this solution is actually cheaper. Although we offloaded the database and the storage operations off-chain, uh, it we uh, we replaced it with a lot of computation. Right now, when we get some kind of a witness, we need to verify this witness, and it requires some non-trivial verification, some non-trivial computation of this witness. It could be linear in the number of database accesses. It could be pretty expensive, and it might be the case that we saved a little bit, but maybe adding this complexity to the system would not be worth it. And it might even be the case that this system is even more expensive to use than the original one. What we will do now is we will optimize it furthermore by optimizing the computation and offloading it off-chain. So for this, we will use Cairo and Stark proofs. The code that before in the previous solution, we said that we want the smart contract to be able to verify the integrity of the database, the values that we read from database with the committed on chain to verify the witness. This code, we offload it as well, and we move it to Cairo. We write this same logic in Cairo. So now what we have is a Cairo program that we send to it the witness. We use it as an input to the program, the same witness we would have used before and send it to the contract. The Cairo program, we execute it. It outputs all the information that we need. For example, it outputs the database hash for the consistency we need with the chain. If we do some change, a new database hash, if we need to make sure we executed some specific read or write operations or to see the values, it outputs it as well. But anyway, we take this execution and we prove it with the Stark prover. And what we send on chain is only the Stark proof. So now a computation that could have been expensive before is now much cheaper to verify because of the properties of the Stark proof. The Stark proof can be verifiable in a logarithmic time compared to the naive execution. And this is where the scalability comes from. So let's just look again at the flow that we have. We move the logic of verifying witness from the Solidity contract to the Cairo program. We prove the valid execution of the Cairo program. We send on chain and verify the proof. And if needed, we update the database hash. Okay, how can we improve more? Before that, so let's analyze this solution. The pros of this is that now we actually get really great gas efficiency. We can batch into this proof a lot of different accesses to the database. It can be a lot of reads, a lot of writes, and moreover, because Cairo is Turing complete, we can offload more parts of our application to Cairo and save even more. And because the proof verification is logarithmic and practically it is constant, we can move a lot of logic and run on this Cairo code a lot more logic than what we could have run on the Solidity contract. The cons of this approach is that it is still complex design. Just as we had before, we need to have an operator. We need to be aware of proving it now. And again, users cannot access the contract directly because everything has to go through the operator. What we have is actually meta transactions. If we want to improve even more, for this we have Sharp. Sharp is the shared prover that we provide. It allows application developers to remove the thoughts, remove the burden of thinking about the Stark proofs and focus on developing the Cairo business logic for their application. Put the business logic they want to prove, to write it in Cairo, and to leave the proving to us, to the sharp proving service. It allows a lot of such applications to send requests, proof requests to a prover, which aggregates them together, and then it generates a single Stark proof, which is verified on-chain in a decentralized manner. So this single Stark proof, remember, is practically constant, but now it can be shared among many, many different applications, what makes the amortized gas cost per application much lower. And it lowers the bar of applications that want to scale using Stark proofs to something much, much lower than what they had before. The verifier, when it verifies a proof, a shared proof of a lot of such applications, what it does is for each and every application, each and every Cairo statement it verified, it keeps on chain a fact, an attestation that it verified this statement, that this statement is indeed valid. This fact, this attestation is actually a hash of the Cairo program that it verified execution of and the output of this program. It actually shows that there is some known input to this Cairo program, making it to output this specific program output. This hash, this fact, can again be shared among many different applications. And if there is some interesting fact, an important statement that was verified once, a lot of different applications can use it again and again in order to in their applications, in their business logic, if they want to do something constrained on this fact. So a bit more about Sharp, the shared prover. So it allows, as we said, economies of scale. We can have a lot of users to share the same proof with independent applications, what lowers the amortized proof cost per user. It allows the application developers to focus on their business logic. The only thing they need to do is to write their business logic in Cairo, as you will do in this workshop, and they can get magically through this service the ZK proofs to scale the application, to scale their application. This service is, in addition, binds the Cairo logic, which is off-chain, with a DApp, an application, a smart contract on-chain, by sending the proof to the on-chain verifier. Moreover, it's not some theoretical idea. It is something that we have live right now, and anyone can use it on Ropsten. You can use it through the playground. We will see an example soon. Additionally, you can use it directly from your computer by installing the Cairo Lang package Alon just showed before. And you can read more about this in the Cairo Lang documentation. In addition to all of this, today we published a blog post showing a use case using this sharp proving for AMM. So the AMM tutorial that you'll get familiar with as well in this workshop, what we did, we integrated it in addition to the Cairo code with a bit more Python and Solidity. We integrated it into a full scalable application using the sharp proving service, and you can see it. It is open source. You can look into it, and you can see exactly how such an application works like. Let's have an example in the Cairo playground and see just the look and feel of what does it mean to use the sharp service. So here, when I open the playground, I have this first application when I open it, and I can change it. I can write any other code, as you've seen with Alon before, and I can prove it. Proving it would send this request to prove this statement to the sharp service. Trust me, I tried this before because this is the first thing any visitor of the Cairo playground sees. A fact of an execution of this program is already registered on chain, and I would like to make it a bit more interesting. So I'll change the program a bit. I'm changing it just by changing this number to something pretty random. And it, of course, it changes both the program and the output of this program. Now I would like to prove this. So I click on prove, and it tells me that I'm about to prove this program with the Sharp service. I click on it. Here you can see that it output for me the program hash and the job fact. The job fact is what I expect to see on chain. The job fact is the hash of the program hash together with the program output. You will see it when you dive into the tutorial. Let's click here to see the progress. So we can see here that the job is currently created in the Sharp proving service, and let's just catch it before it is proved and make sure that the fact is not registered on chain. So here we just go to the Sharp verifier contract, and we check this fact, and indeed it was not verified on chain yet. Let's wait. I think it could take about a minute or two, maybe even less, for it to get verified on chain. Meanwhile, until it will be verified on chain, I'll take a look at the chat if there are any questions to address.
Moody asked about the Cairo program.
I see. That Cairo program output included in the fact include all the initial state, input, and final state? No. The Cairo output is what you as a programmer define it to include. This is fully applicative thing that, as let's look here in the program. So you can see here there is some output pointer. You can think of it as an output tape, and you just write to it values. This is what defines the output of the Cairo program. And why would you want to use an output? You would like to use an output when you want to communicate, for example, when you use Sharp, when you want to communicate something to your on-chain contract. Because the fact the Sharp generates is a hash of this output and the hash of your program, you can write a smart contract that later, when the fact is generated, you tell it, here, the program that you probably know because this is the business logic, so you know this hash already of this program. I know some input to it that made it to output this specific thing, this specific list of values. What the smart contract would do, it would hash this list of values together with the program hash and verify on the Sharp verifier contract that this fact is indeed registered there. And let's see here again. Yes, it is registered on chain. So before, when we checked, we got false. It was not registered yet. Now we have true. So the fact is registered on chain. Okay. Let's see if there are any more questions about it. Is the program hash proven inside the Stark proof? Yes. So if we look here at the Sharp, this is a very good question. If we look here at the Sharp system, when we have a lot of different programs, which are independent programs, sent to this Sharp proving service, what we actually implemented in the Sharp proving service is something that we call the bootloader. You can think of it as kind of an operating system that runs a lot of different programs. So what it does is it loads to memory the program that you want to prove, you want to execute. It computes the hash of this program, it executes this program, it gets the output of the program, and it outputs the output of the program together with the hash. So the output of the bootloader, the output of this big Cairo program that is proven in this sharp proving service statement is actually a list of pairs of program, Cairo program hash, and its output. This is what we get, and this is indeed proven. This is part of the proven statement in the Stark protocol. Yes. So Sharp will aggregate the facts for different programs and users, somehow create checkpoints for just so Sharp will aggregate the facts for different programs and users, somehow creates checkpoints. I'm not sure that, Nathan, I'm not sure that I understand the question about the checkpoints. We have something about checkpoints, but I'm not sure if this is exactly what you mean here. But if I'll try to answer it this way, yeah, so for each and every program, we have kind of a checkpoint when we stop, when we execute it, and we add to the output of the bootloader the information about the hash of the program and the output, and we move to the next program to prove. I'm not sure if this is exactly what you meant.
So every program generates a single fact independent of the other programs.
Okay. In which platform is the Sharp installed? So the Sharp service is something that we run on our services, but what you use, the Cairo Sharp, is a client of this service, and it is written in Python, and we tested it on a Linux-based system. I'm pretty sure that you can run it on Mac as well, and I would guess that you can run it on Windows, but I personally did not test it on Windows. Are the outputs in the fact hash organized in a Merkle tree such that I can generate a Merkle proof for them? So there is some more complex structures that you can share information with the on-chain state using some kind of hash trees, but I prefer not to dive into it here. Does this Sharp service runs on a centralized server? Yes, the Sharp service runs on our server. It's not something decentralized. Are there any plans to open source the Sharp service so other entities can also run their own instances? So we in Starkware have plans to open source the Stark provers. This is the part of our roadmap. This is part of our roadmap for Starknet, which I believe you heard of before. And actually, Starknet is planned to reduce this need in an off-chain operator as we have here today. One of the goals of Starknet is to reduce this need. Specifically, if we plan to open source the backend of Sharp with all the logic behind her, this is not something that we currently plan to do.
But we do plan to open source the prover.
Yes. Yeah. Yes. Thank you.
Sorry, I don't quite understand. If it's not open source, it doesn't really have to be open source, but surely the program being proven has to be at least visible. Otherwise, how does anyone know what the verifier on the chain is actually checking?
Yes, so you are absolutely right. The proof is publicly available. First of all, the bytecode of the bootloader program is something that is on chain. You can see it on chain. Moreover, the code is publicly available in the Cairo repository. Lior, is this correct?
The code of
The bootloader.
so currently the code is not available. I guess we will open source it. Yeah, but of course the code of any programs that you run should be open source. You know, for the users to trust it. Yeah, you're right.
Okay. Yes. If Sharp is a central service run by you.
By the way, I want to add that so only the hash of the program is going to be visible when the proof is registered on chain, which means that it is possible if for some reason someone wants not to reveal the program, then it is possible to do this with Sharp. But it also means that if you do want people to trust you, you have to publish the source code of the program, the Cairo source code, and then people should compile it and make sure that the hash is corresponds to the value that's on chain. And this is something that we did with the Cairo the code for StarkX 2.0. And you can find the code for StarkX 2.0 in the repo, and with a test that shows that the hash of the program is indeed the hash that's stored on chain.
Okay, thank you. I'll continue with another question. If Sharp is central service run by you, can I guard against it going down? Can I run my own that would be a replacement then? So of course, when it is a centralized service that we run, then nobody can guard that it would not go down. It is of our best interest, and we want to make sure that it would be highly available and would work. And of course, as we said before, we do have plans to open source a Cairo prover, a Stark prover that can prove Cairo programs, and then anyone can run a replacement for this service as well. Starknet, is it correct to say that the verifier need not trust the prover and therefore the Sharp? Right, this is correct. It is sufficient to read the verifier code, to read the bootloader Cairo code that the verifier here verifies, and no need to see the prover code. This is correct. Is Cairo? Yeah.
Go to the next question. I just want to maybe correct something. We said, I think we said to open source. I don't think this is the correct term. So we are going to open the Cairo prover, and there is a planned license for this, which is already available. So you can check. It will basically allows you to run the prover as long as you send the result to a specific verifier on chain, which will basically, the idea is to make sure that it's not possible that your application will stop working if Starkware is down. This is what we aim to guarantee.
Yes. Okay. Lior, thank you very much for this correction. Yes, indeed. My bad. Yes, it's a specific license that you can read on in our website. Yes. Just because I have one last minute, I won't dive into more questions. I try to continue answering them offline. I'll just summarize. So we've seen here that Stark proofs can scale your decentralized application. We've seen that Cairo can be used to describe your business logic, and Sharp is the tool that can connect your Cairo business logic with your application smart contract on chain, and it does it using Stark proofs. Thank you very much for your attention.